Pulse width modulation, often shortened to PWM, is a clever technique used in electronics to simulate analog signals using digital means. Imagine a light switch that you can rapidly turn on and off. With PWM, we're doing something similar, rapidly switching a signal between on and off states. However, instead of just on or off, we control the amount of time the signal is on or high versus off or low. This on time is called the pulse width. By adjusting the pulse width, we effectively control the average amount of power delivered. Think of it like dimming a light. A wider pulse width means the light stays on longer within each cycle, making it brighter. A narrower pulse width means it's on for less time, resulting in a dimmer light. This ability to mimic analog behavior using digital signals makes PWM incredibly useful in a variety of applications. From controlling the speed of motors to adjusting the brightness of LEDs, PWM provides a versatile and efficient way to interact with the physical world. To grasp the concept of PWM, let's visualize a simple example. Imagine a water faucet that we can rapidly turn on and off. If we want a slow flow of water, we turn the faucet on for a short burst, then off for a longer period. This cycle repeats, giving us a controlled but reduced flow. Now, to increase the flow, we simply keep the faucet on for a longer duration in each cycle. The water still flows in bursts, but the longer on time means more water is delivered overall. This is essentially how PWM works, but instead of water, we're controlling the flow of electrical energy. The ratio of the on time to the total cycle time is called the duty cycle. A 50% duty cycle means the signal is on for half the cycle and off for the other half. A 25% duty cycle indicates a shorter on time, and so on. By adjusting this duty cycle, we precisely control the average power delivered, even though the signal is constantly switching. Microcontrollers, the tiny computers embedded in countless devices, heavily rely on PWM for interacting with their surroundings. Since microcontrollers are inherently digital, they excel at generating the on-off patterns that constitute PWM signals. These PWM signals can then be used to control a wide range of external components. For instance, by connecting a PWM pin of a microcontroller to a motor driver, we can regulate the motor's speed. Similarly, PWM signals can adjust the brightness of LEDs, control the volume of a speaker, and much more. The beauty of PWM lies in its efficiency. Because the signal is either fully on or fully off, there's minimal power wasted as heat. This is particularly beneficial in battery-powered applications where energy efficiency is paramount. The versatility of PWM is evident in its widespread use across various industries and applications. Let's explore a few real-world examples. Motor speed control. PWM is extensively used in controlling the speed of DC motors in devices like fans, power tools, and robotic systems. LED brightness control. From dimming the screen of your smartphone to creating vibrant LED displays, PWM allows for precise control over LED brightness. Audio amplification Class D amplifiers, known for their efficiency, utilize PWM to generate audio signals, delivering high-quality sound with minimal power consumption. Solar charge controllers. PWM techniques are employed in solar charge controllers to optimize the charging process of batteries from solar panels. These are just a few examples of how PWM, a seemingly simple concept, plays a crucial role in shaping our technological landscape. Its ability to bridge the gap between digital signals and analog control makes it an indispensable tool in countless electronic devices and systems.